Also wanted to look at a resistive type of fault current limiter. In the case of a resistive fault current limiter, we have a superconductor or other nonlinear type of device. If the current exceeds the critical current in the superconductor, then the fault current is going to be reduced here. Okay. Once again, can superconductors have visco tubes that are designed for this purpose here, and you can see, for example, the current versus temperature characteristics, the critical current versus temperature. There will be Joule heating in the resistive fault current limiter as well. So I wanted to illustrate some of the QuickField capabilities that can be used for solving this type of problem. In this case, I have an axisymmetric problem, and this is the z-axis. I look at my properties. This axisymmetric, we have 50 hertz excitation, AC conduction. In this case, I've just given the conductivity rather low. We have opposite potentials. And once again, this is going to be a region of zero normal current density. Okay, on the side boundary, there's zero normal current. So I believe the problem's already been solved, but it's a very small problem here. And as well, we can look at a vector plot of the different phases of the current density here. What I wanted to do was couple this to a thermal problem and look at some of the heat transfer characteristics. Now, when we couple it to a thermal problem, we're going to export the Joule heating here into the thermal problem, and these have to share the same model file. So the same model file that we have for this one is also shared with the thermal field problem. Okay. So in the case of the thermal field, it's the same model file. Okay. We have coupled the generated heat from the resistive limiter problem. Now I have some thermal conductivity of the element here, thermal conductivity. These would be used for a transient heat transfer. Now on the edges of the superconductor, I'm applying both a convection and radiation boundary conditions. So the external temperature here is at 77 degrees. We have a convection coefficient of 10 and an emissivity pretty close to 1 in this case. So this is both convection and radiation. The same boundary conditions are applied here to both sides and also on the sides of the wall here. Okay. So now in order to couple the heat transfer under problem properties, we would go to links and then include the link here. So we would browse for the heat generated by the first model and then include it here. Okay. So it's already been solved, but let's go ahead and look at the solution again. Okay, so this represents the temperature field. Make that full screen. As well as we can look at the heat flux vectors here. This represents the heat flux vectors that are flowing here.